Let's talk about malonic ester synthesis. So malonic ester synthesis is a really cool reaction, and it starts out by using this diester, which we call diethylmalonate. And when you take diethylmalonate and you treat that with sodium methoxide, you can imagine, since the protons here on this carbon are so acidic that they get deprotonated rather easily. And I'll just draw this quick and dirty here, that we can deprotonate that, and we generate a doubly stabilized enolate. And I'll draw the enolate out with the negative charge on the carbon. As you can imagine, you could draw out 3 different resonance structures for this molecule. You could draw this one, and you could draw one where the negative charge is on either one of these carbonyls. So the first step is deprotonation, and that reaction is irreversible because the proton is so acidic. So once we have this, once we've generated this enolate, this can act as a nucleophile to react with an alkyl halide. So if you take and you do this reaction with an alkyl halide, for example, you'll get an SN2 reaction, and what you will get is you will get an alkylation at that carbon in between our 2 ester groups. So look, we'll get alkylation here. And you could actually do dialkylation because there's still a proton here, but we're just going to look at monoalkylation right now. So now we have our monoalkylated product. So once we have our monoalkylated product, I'll just move it down here a little bit. So once we have our alkylated product, well, you know what happens when we treat an ester, what happens when we treat an ester and we treat that with H3O+, and if we heat that up, what happens when we treat an ester with H3O+ and heat? That means we're going to hydrolyze the ester to get a carboxylic acid. So then we're going to end up with a compound that has 2 carboxylic acids in it, okay? So we end up with this dicarboxylic acid. But what's interesting about this dicarboxylic acid is it is not stable the way it is. Whenever you have an alpha-beta carboxylic acid, so how would you say this? A 1,3 dicarboxylic acid. This is an unstable compound which undergoes decarboxylation. So whenever you see this kind of functionality, you have a carboxylic acid and another carboxylic acid adjacent to it with only 1 carbon in between them, and you heat that up, what actually happens is you get this, what I call a decarboxylation. And you can redraw the molecule. Let me grab my pen here. If you redraw the molecule like this, the mechanism is really a fun mechanism to draw, and it's really simple. And what happens is that you actually end up losing carbon dioxide from the molecule, and you end up basically with a substituted acetic acid. So you could draw the mechanism like this, where we take this proton and then we form this bond down here. So this is after heating it. So we heat it. And what do we get when we do this? Well, let's see. Let's draw our product. So we've lost CO2. So that came from here. This is our CO2 that we lost. And what do we have? So we have our carboxylic acid intact, and we formed a yeah, that's not right. We have 2 hydroxyl groups here, and then we have a double bond over to our R group. But we know that that is not going to exist like that. That is going to tautomerize. It undergoes a tautomerization, which is going to lie heavily to this side to form a carboxylic acid with an R group attached to it. So essentially what you're doing is you're adding 2 carbons to your R group, and on the second carbon there's a carboxylic acid. And that's why I wrote this at the top of the page where it says malonic ester synthesis. Basically what you're doing is you're taking an R group and you're adding 2 carbons to it. So basically you're making a substituted acetic acid. In essence, what you're doing is you're making a substituted acetic acid where you have an R group off of an acetic acid. And these are the 2 carbons that come from the diethylmalonate after the decarboxylation. So it's a really fun mechanism to draw, and you can also do dialkylations so that you would end up with 2 R groups at the end. And basically, in order to end up with a second R group on your molecule, all you would need to do is you would just need to do a deprotonation again and add a second R group. So this is a way that people make functionalized acetic acids. Malonic ester synthesis.